For most of human history, it was the only source of light in the absolute dark of the night, a constant, glowing companion tracking predictably across the sky. Ancient cultures viewed the moon as a divine, mystical object, a flawless sphere of light that existed outside the realm of physical reality or human reach. The prevailing thought was that Earth sat motionless at the center of the universe, surrounded by nested mathematical spheres. Everything above us was considered static, orderly, and perfectly divine. That assumption of perfection created a massive blind spot. It kept early thinkers from realizing that the space surrounding our planet is actually incredibly chaotic and violent. As long as we treated that light in the sky as an object of worship, our understanding of the cosmos went nowhere. Progress required taking a much closer, deeply critical look. The breakthrough came in the early 1600s, when inventors figured out how to grind glass into magnifying lenses and eventually pointed them away from the horizon and up into the dark. Galileo Galilei took one of these early optical tubes, refined it, and aimed it directly at our closest neighbor. Through the glass, the illusion of a smooth, divine sphere shattered. He saw jagged mountains, deep valleys, and massive circular craters scarring the surface. Here on Earth, wind, rain, and tectonic plates constantly erase evidence of impacts. Up there, with no atmosphere or weather, those ancient craters had sat perfectly preserved for millions of years, waiting to be seen. Seeing a rugged, physical landscape proved that the heavens were made of the same ordinary rock and dust as the ground beneath our feet. It was the crucial first step in realizing Earth was simply one of many regular planets in a much larger system. Mapping the physical terrain was only the beginning. The next puzzle was figuring out exactly how that massive rock was moving through space. By observing the precise geometry of lunar eclipses, astronomers could calculate the angles of the shadows. Calculating these distances gave us the first mathematical scale for the space beyond our atmosphere. Knowing that distance allowed Isaac Newton to correlate the moon's orbital speed with the Earth's mass. It was the first time we could quantify the pull of gravity on a planetary scale. This wasn't just a local phenomenon. The exact same mechanical force holding our neighbor in its stable orbit is what dictates the paths of distant gas giants and even the extreme physics of black holes. The moon provided the first environment where the math of the universe could be verified outside of Earth's atmosphere. It proved that the mechanical laws we observed locally applied to the entire cosmos. Fast forward to the 20th century, and looking through lenses was no longer enough. We built 3,000 tons of controlled explosives to physically go there. Leaving the atmosphere required an incredible leap in engineering and precision tracking, relying on rooms full of technicians computing orbital trajectories in real time. The primary scientific imperative of the Apollo missions was to pry pieces of the surface loose and bring them back home. Back in sterilized laboratories, geologists slice these samples incredibly thin to analyze their chemical composition and the history of their physical trauma. The isotopic signatures inside those rocks matched our own planet's crust. They pointed back to a massive, fiery collision early in Earth's history that threw molten debris into orbit. When scientists dated these samples, they found that the most intense scarring occurred simultaneously across different landing sites. This synchronization revealed a specific, chaotic era known as the Late Heavy Bombardment, when the entire inner solar system was flooded with debris. Without weather to wash away the evidence, that battered, airless surface operates as an untouched museum. It holds the perfectly preserved record of how our solar system was actually born. If you look up tonight, the view hasn't changed since antiquity. The silver light and dark patches are exactly what the earliest humans saw, but our comprehension of it is entirely different. Every visible feature, from the dark plains of hardened lava to the bright highlands to the sheer speed of its orbit, can now be read. It is a decoded map of celestial mechanics and ancient geology. We started out looking up in absolute mystery, trying to guess at the nature of the heavens. Now we look out with mathematical certainty. Studying that rock next door ultimately revealed our own scale. It allowed us to accurately measure and place Earth within a vast, dynamic system. Our closest neighbor provided the first legible record of the system's history. By learning how to interpret this one landscape, we finally learned how to understand the rest of the universe.